We're going to pick back up in section 3.2. We had started talking about addition of whole numbers, had run just a little bit of definitional kind of things at the beginning, and we left off where we were going to start taking a look at properties. So there are four basic properties of whole numbers that we're going to discuss. The first one's called the closure property. The closure property is probably the one that we take advantage, or not take advantage, take for granted is what I want, take for granted the most. The closure property says that if you have two whole numbers, A and B, and you add them together, you get another whole number. That's not just nothing. We take it for granted all the time, but it's not just nothing. It's very specific to addition, and it's very specific to whole numbers. For example, if you add two fractions together, you do not always get a fraction. If you subtract two whole numbers, you do not always get a whole number. So the fact that it's addition and the fact that it's whole numbers makes this happen. The commutative property and the associative property are the two that you've probably heard about the most. Commutative has to do with the order of things changing, and we don't take this one for granted because we use it a lot, and many of you are going to use it intensively with children at the young grades, particularly with addition, because A plus B is equal to B plus A. So that makes memorization of simple math facts so much easier, right? So the kids who are working with flashcards and they're doing all their plus ones, right? And then they're doing all their plus twos. At some point when they're getting up to the plus nines, while it should be hard, it's not, because they've memorized them all along the way with the other lower values. And so this commutative property makes things very, very friendly for us. The associative property, we don't use it quite as frequently, but there are cases where it's very useful. It talks about the order of things addition. So if we take A, B, and C, leave them in a static order, you can switch the order, but that's the commutative property. We're talking about the associative property here, so as long as you've got them in the same order on the left and the right. The associative property tells you what's associated together. So on the first piece, you see the A and the B being associated in the parentheses. And on the second side of the equation, you see the B and the C being associated on the side of that side of the equation. The reason that that's nice is because sometimes there are numbers that are easier and nicer to add together than others. For example, if you had three numbers and you actually wanted to add them together and you happen to notice that one of them was an 8 and one of them was a 2, it'd be nice to add the 8 and the 2 together first, because 8 plus 2 is 10, and 10 is a very nice value to then add to other things. So there's sometimes a very reasonable ness to choosing to do it in a different order than it's necessarily done from like left to right or the parentheses as they're given. The identity property, and if you would, I'd like you to write the word additive identity. These are all additive properties, but the reason that it matters here is because this additive identity is different than the multiplicative identity, whereas the additive property of commutativity is exactly the same as the multiplicative property of commutativity. You just switch the numbers, okay? But with the additive identity, we actually have a specific item that we're talking about, the additive identity element, namely the number 0. And when we talk about the multiplicative number, it's not going to be the number 0. So this property says there's a unique whole number 0 called the additive identity, such that for any whole number A plus 0 is equal to 0 plus A is equal to A. Okay? You know it to be true. It kind of feels like, well, why do we want to add 0 to stuff? Well, it's actually more helpful than you might imagine, because when we do it, we don't think about us doing it. We just do it naturally because it makes sense to do it. So I'll point along the way when we come across those kinds of things inside of our algebra. For starters, though, what we're going to do is simply identify which property is present. So you've got 4 examples, and I'm going to just be quiet for a minute while you fill them in beside them. Do your best to predict is the word I wanted to, predict which property it is identifying for you. So you have 4 properties and you have 4 problems. That doesn't necessarily mean they're all used exactly once, and so forth. So write down which property you think is being described by A through D. Once you've written your answers down, turn to somebody nearby and just compare notes. If you're different, see if you can figure out which one of you has the right idea. People are like looking around, so find somebody else who's looking around. There is only one on each of them. Mm-hmm. Yeah. Sorry. We use them merged all together all the time, though. We do that. All right, let's see what you guys got. What do you think the first one is? Commutative. It is commutative. Very good. By the way, the word is commutative, not communicative. People write down all sorts of weird words. That's the one that people always change. They change it into some other word, and it usually means something different. And I'm like, oh, that wasn't the right word. Commutative, as in you are commuting. How about the second one? Identity. Yeah, it is the additive identity. So please do make sure you've got that word additive there. Additive identity. How about the third one? C. It's commutative. The reason it's not associative is because what's paired together doesn't change. So the associative property changes what's being paired up, and this one didn't do that. But the order of the pairing is switched, right? One place it's 6 plus 8, the other one's 8 plus 6. So this is actually commutative as well. How about D? Yeah, that one is associative. Don't go abbreviating that word. The associative property. All right, any questions on those? Sometimes they will create the problem where they also have you fill in the blank somewhere to make the statement equal, and then they tell you to write the property. You'll see that sometimes too. All right, so what we're moving into next are some addition strategies and then algorithms. So basic addition strategies, these are ways that we often teach young children when they're first starting to count, how to use counting to help them with addition. And so the first one is called the counting on strategy. So you start with one of the values and you count up the additional amount of the other value. And you've probably all used this strategy. It's a really common one. And so you're doing something like, 5 plus 3. And you usually start with the bigger number, say 5. And then you go 6, 7, 8. And you count it up 3 and now you're done. That's the counting up strategy. Doubles is actually one that you may or may not have ever seen used. But it is most definitely taught and has been for a number of years now in curriculum. So the idea is that if a student knows all their doubles, and they often will learn them first, they'll learn what 0 plus 0 and 1 plus 1 and 2 plus 2 and 3 plus 3. They'll learn all the doubles first. And what they do with that then is that the idea is that they can take something that's a near double and they can use what they know about doubles. And I've seen my daughter who's in second grade use this the entire way. I mean, like it's hugely in the curriculum that her classroom's using. So when she looks at 3 plus 4, she'll say, it's a near double. So I just need to do 3 plus 3 and add 1. And that's how she thinks about it. So you don't necessarily have to love the strategy, but for some kids, I think it's a really good tool and it does work. For my daughter, it works really well. A third one that I mentioned a little bit before about making tens, actually makes tens instead of it just already having tens. So it looks something like this. The idea is learning all of the numbers that add together to make 10. So we know that we can have 2 plus 8 and 3 plus 7 and 4 plus 6 and 5 plus 5. So when we have something that's not one of those, but it's close, we can take something like 8 plus 6 and say, okay, well, I know what 8 plus 2 is. 8 plus 2 is 10. And then to go from 2 up to 6, I just have to have 4 more. So I'm breaking the number 6 up. What I'm really doing is breaking the number 6 up into the 2 that adds to the 8 to give me 10, and the 4 that's left over when I didn't do that. So making 10 is another strategy that we see used in curriculum today. So the next thing we're going to actually do is talk about algorithms when you are working with numbers that are slightly larger. So these strategies are sort of like basic addition, single digit addition stuff, right? The ones that I just talked about. The difference between that and the next portion is we're looking at values that are larger. Something where you actually have to do a calculation, not just have a memorized fact. Okay? So there are several addition strategies. The first one that's a concrete model, really good for kinesthetic, touchy-feely, beginning strategies of things, why it actually works to do some of the other things that we do. So this example says we've got 34 plus 18. And if you'll remember last class, or maybe a couple class periods ago, I showed you the red base 10 blocks. You guys remember that? That's what we're using for the concrete model. And you could use other things. You could use, money. I mean, money would work for a concrete model perspective as well. But our base 10 blocks work really nicely because they have the size factor that our money doesn't. Money can sometimes confuse children because pennies are bigger than dimes but worth less. That kind of stuff kind of throws kids. But with base 10 blocks, we've got a size visual picture that makes it make more sense. So when we're looking at the number 34, we're actually going to draw 3 longs. And they do not need to be perfect. The visual is what you're going for. There's 3 longs. They're supposed to be all the same size. And you've got 4 units. So you have 1, 2, 3, and 4. And I've got the number 18, which is 1 long. And I've got 8 units. So I have 4 and 4 more. So the idea is that I'm taking 34 in its sort of picture form and 18 in its picture form. And if you were really using this in a classroom, you wouldn't even draw the pictures. You'd actually have children playing with blocks, right? They would really physically do this. And if they had the base 10 blocks, which are not the kind that I have, where you could actually connect them together, that'd be even better. Because what we really want to do is we really want to take these 8 and a couple more of them, and we want to merge them all together and to create a long. Okay, so I take those pieces, and I'll even change my color just to show you that I'm doing that. And this is my new long piece that I've created out of the 10 individual units that I circled. But there's also other pieces, right? I still have the first 3 original longs, 1, 2, and 3. And I have the 1 additional long from the 18. And I still also have these 2, oops, I didn't mean to do that. These 2 blocks right here that are not grouped up that need to be included. And then this would be my total when I'm done. And we can count them up. How many longs do I have? 5. And how many units do I have? 2. So this is the number 52 from a concrete model perspective. The next one is the one that you know and love, so to speak, because it's the one that's always taught. It is called the standard algorithm. I guess I didn't get it cleaned out from last time. The only one I didn't. So the standard algorithm has what we probably, at least probably most of you, referred to as carrying. Did anybody use carrying the word? Yeah, you never see the word carrying written in any kind of curriculum now. It's always called regrouping, by the way. Which I understand the descriptive phrases of both, but what it's actually meaning is better phrased with the word regrouping. So the idea is that we start with the ones place, and we say 4 plus 8 is 12, right? And so what we did back in the day, or even now, is that we write down the 2 and we carry the 1. But what they would actually say now is that you had the number 12. The number 12 is 10 and 2 ones. So you regrouped the 10 into the tens column. It was 110. and you had your 2 ones left over. That's the language that's being used, which is far more accurate, really, than what we have used in the past. Then we can add the numbers in our tens column, 1 plus 3 plus 1, and we get the number 5. So that's the standard algorithm. The nice thing about the standard algorithm, it's very quick, right? The whole point is that it's efficient to use. But it does look a little bit mysterious. I just changed the number 12 into 1 and 2. I moved the 1. I wrote down the 2. What if I did it backwards? I mean, like there's inherent sort of, issues that present itself with efficiency that can come into play when you're doing this. Kind of a compromise between the concrete model, which is our picture form, the one we just did, and the standard model, which is more efficient, is a model called the expanded algorithm. And I actually was speaking with someone, you guys know Hallie Walker? Okay, so she's another education major. She's in my contemporary class, and she was talking with me this morning about going to a second grade classroom recently, and this is what her teacher had her teach, and she was so very excited because she remembered learning it last fall when she took this class. So she actually saw it in play and how it worked with the kids in her classroom. So if you know her, you might check in with her and see how that went. But the way that this works is we take the number 34 and the number 18, and we break it into its place values, 30 plus 4, 10 plus 8. And what we do, I'll actually write it a couple of different ways. You don't necessarily have to write it all these different ways, but there's different versions, is we add things up place value-wise. The nice thing about this is that it doesn't matter if I add from left to right or right to left. That's actually fairly friendly because most of our mathematics is done counter to what English is read. And you may not have thought about that before, but that can cause problems for kids. We're reading from left to right, but we're doing math from right to left. That's weird. So this way would allow you to actually go from left to right if you wished. 30 plus 10 would be 40. And then 4 plus 8 would be 12. And then what you really do is you break the number 12 down just the same way as before. So here's my 40. The number 12 is 10 plus 2. And then you're able to combine the 10 and the, I don't know that I need a line there, but the 10 and the 40 to make 50 plus 2 and to make 52. Now before anybody asks, do I have to show all of the steps? No, you don't have to show every single piece of that. But the whole breaking down is the point. We're breaking them into their individual place values, and then we're combining the place values together. Any questions on that? Now, I mentioned that this was kind of like the concrete model, and you may not have sort of thought about it as you did it, but we had 12 units, 12 little blocks, and we created 1 long and 2 blocks, right? That's the 10 and the 2. And then we joined the 4 longs and the 1 long to make my 5 longs. That's what we actually did in that picture form before. All right, we have a few more. Column addition. So column addition actually does similar things to what we just did before. It also allows you to add from left to right. So we've got a little bit bigger numbers. You see it play here. We've got 1,534. 3,218, and I am writing them sort of as a vertical addition problem. And I can move from left to right. So what I'm really doing is I'm adding the 1 and the 3 together, much like I added the 4 and the 3 and the 1 together here, the 30 and the 10. I'm just not writing it out. So when I add this first one together, in some sense in my mind, I'm thinking that I'm adding 1,000 plus 3,000 because I'm adding the thousands column. And what is 1,000 plus 3,000? 4,000. So I won't write down all the additional steps, the addition steps on the side to show it, but that's what you're thinking every time. I have the 5 and the 2, it's 500 and it's 200. What's 500 plus 200? 700. I have a 3 and I have a 1, that's 3 in the tens column, so it's 30 plus the 1 there is 10, so 30 plus 10 is 40. My last column we've done several times now. We have 4 plus 8, which gives me 12. What you notice in this is not efficiency. I mean, this took several steps to write it all down. It's not super efficient. But you see lots of zeros, which are really easy to add with. And that's pretty friendly because now I can actually add with lots of zeros. So when I look at the ones column, it's just a 2. And I look at the tens column, I have a 5. The hundreds column's a 7. And the thousands column's a 4. So I have 4,572 by focusing on the columns themselves, the place value columns. All right, the next one is it'll have a form actually inside of multiplication too. It's called the lattice algorithm. I'm going to write it much like I did the previous one where I wrote 1894 and 3218 like this. And underneath it, we're going to draw a box. And our box needs to be split into 4 because I am adding 4-digit numbers. So however many digits your numbers are, that's how many splits you're going to have in your box. The other split in your box is going to be diagonal splits, and that's what creates a lattice. Mine isn't lining up super well because I didn't draw it very good, but hopefully we'll still get the idea. It doesn't matter if you go left to right or right to left at this point again, because you're just adding the columns together. So when I add 1 plus 3, I'll just go from left to right. I get the number 4, and a single digit goes in the bottom corner. 8 plus 2, however, gives me 10. That's a 2-digit number. So I put the 1 in the top corner and the 0 in the bottom corner. Nine plus 1 is 10 again, so 1 in the top corner, 0 in the bottom corner. The last one, 4 plus 8 is 12, so I have a 1 and a 2. Is everybody okay with that? So what that does is it actually creates the tens column, but it creates it in a diagonal form. So take a look at what's happening here. I'll change colors to show you. This column right here at a diagonal is actually the tens column. The 1 in the top right corner of that furthest most box on the right is actually the 1 from the number 12 in the tens column, right? It was the 10 from the number 12. And the 0 is the 0 from the number when I added the 1 and the 0 together in the tens column. It's 0 tens. So what we do is we'll expand each of our diagonals, and now we actually do need to add from right to left. So we add along our diagonals. This is a 2, a 1, and a 5. If we had exceeded the number 10, we would carry or regroup, just like we would have in the standard algorithm. So if one of these diagonals added up to, say, 12, we'd write down the 2, and then we'd move the 1 over to the next diagonal column. All right, this is tons of just like me showing you lots of things. So how are we doing so far? So far, so good? Okay. We have a couple more, I believe. Opposite change is the next one. Opposite change takes numbers and it makes them nicer. So these numbers are not what we would consider nice numbers. The nice numbers showed up over here when I had lots of zeros. Those are nice numbers because it's nice to add with zeros. So our goal when we're looking at 488 and 231 is really to get one of them to have the first digit as a numerical value that's not 0 and then 0 everything else out. So I'm going to deal with 488. You could deal with 231 the same way, but I'm going to deal with a 488. And notice if I were to add 2 to this number, 488 becomes 490, and that's better than it was before. We're just dealing with one digit at a time. Don't go to getting too creative here. I know you could add the number 12 and get to 900 immediately or to 500 immediately, but that's probably not how your children would be thinking about it in your classroom. But adding the 2 to get to the 8 to get a 10, remember the making 10 strategy we talked about before, is something they're already familiar with. But I can't just go adding 2 to stuff. I have to compensate. So I'm going to do the opposite change. The opposite would be to subtract 2 from the other value. So I've got 231 minus 2. And what is 231 minus 2? 229. Now we're going to do the same thing again and try to get a 0 on the first number in the tens column. So I would add the number 10 to 90 to get it to be zeroed out. So 490 plus 10 would give me 500. And to compensate for that, I would need to subtract 10 for the other value. So what's 229 minus 10? 219. And the beauty is that at this point, we have zeros everywhere except for the first digit, right, in one of the numbers. So we can have the 9, we can have the 1, and we only have one place value where we actually have addition where there's not a 0. 5 plus 2 is 7. Now the fabulous thing in what we're doing is that you should be able to figure out using a calculator or using the standard algorithm that you've gotten every answer correct. So if you're a little uncomfortable with this opposite change strategy, just check it with the method you know and can just check it with to make sure you got the right answer at the end. We can always go back and look along the way in terms of your work to see are you using the strategy correctly, but we'll know we got the answer right at the end. The last one is I think it's the last one. It's the last one on this page anyway. Yeah. It's a very interesting strategy. And it's actually really helpful, and I use it a lot. But it's only used when you're adding a bunch of numbers together, right? Like you would not use scratch addition to add two numbers together, right? And that's what I've done. Every problem before this has been adding two values together. Some are bigger than others, but they're still just adding two values. So the change that you see happening here is I'm adding 4 values together. They happen to be 2-digit numbers, but it doesn't matter how many digits they are. It has to do with the fact that I'm adding 4. So I'm going to write them vertically just like we did a moment ago. I have 34, I have 18, I have 69, and I have 87. Okay, so here's the way scratch addition works. First of all, you're going to start in the ones column, and you're going to start from the top, go down. Okay, just like you would with like a standard algorithm. And you're going to say, what is 4 plus 8? 12. And what you're going to do is, because you got a 2-digit number when you added, you got the number 12, is you're going to scratch the number 8, and you're only going to remember the 2. Now, you don't really need to write it down. I'm just going to write it down so that it's in there and you see what you did later maybe. But it's 2. I'm remembering the units digit. The scratch is almost representing that I am removing 10, or I'm ignoring the 10. Okay? I'm going to take the number 2 now and add the next number 9 to it. So what's 2 plus 9? 11, which is again a 2-digit number, so I'm going to scratch. And I'm going to write down the units digit, the 1. And then I'm going to add 1 plus 7, and I'm going to get 8. So why in the world would we want to do that? Well, it kept the number smaller that I was continuing to add. Because if I didn't do that, it would have sounded an awful lot like this. 4 plus 8 is 12. I know that because I learned all my single-digit addition facts, but now I've got to add 12 plus 9. And maybe that one's still okay, because maybe you added up to 12, and you're like, okay, that's 21. But 21 plus 7 is not a number, like memorization fact, that any child has ever memorized. Right? At that point, they're probably counting on their hand because they didn't know how to do 21 plus 7 in their head. Okay? So what do we do at this point, once we've ignored these numbers and done these scratches? Well, we count the number of scratches. So how many scratches did I make? 2. And I regroup the 2 scratches that represented the number 10 twice into the next column, the tens column. And I'm going to do the same thing again. 2 plus 3 is 5. Good with that, sorry. Plus 1 is 6. Plus 6 is 12. That's a 2-digit number, so I'm going to scratch. And I'm going to remember the number 2. Because it was a 12. 2 plus 8 is 10. That's actually a 2-digit number as well, so I'm going to scratch. And I have the ones digit, which is a 0. Right here. How many scratches did I make? I made 2. So I will write the number 2 in the next column over. I know there's nothing there right now, but we can write it there anyway. There's a 2 there. This 2 right here is not in the column. Remember, that was what I wrote down as my reminding, the units digit, whatever. So I don't usually write any of these to the side, but I have seen students do so, so I thought I would make sort of note of it, that you can if you wish. But in this column now, the hundreds column, all I have is a 2. So this number is 208. It keeps the addition smaller along the way, is what it really does. So we've talked about the fact that the reason that we're working in other bases from time to time in this section of material, in this chapter, is because we want to put ourselves a little bit in that uncomfortable position that our kids are in when they first learn to do addition. because it feels just so obvious to us because we've been doing it for so long. So we're going to look at it from the perspective of it not feeling quite so obvious. So we're going to add a few problems. You're not going to have a ton of them in the other bases, but a few problems to try to put your mind back in that position of feeling a little uncomfortable. So remember, we have the base 8. It's the digits 0 through 7. And we're going to add 3, 4 base 8 plus 1, 7 base 8. And I'm going to show it to you in a couple of ways, right? A couple of algorithms so you can see how they interplay and how they might be more useful in one algorithm versus another. So the first one I'm going to do is actually, I'm going to do both of them, all the ones I'm doing, I'm going to show you the standard algorithm, but we're going to do this in the standard algorithm first. And we start with the ones column, just like we would, with all the others, okay? So what is 4 plus 7? It's 11, right? Everybody agrees 4 plus 7, I would have 11, but I'm regrouping them into a group of 8, right? So if I take the number 11, how many groups of 8 do I have? One group of 8, so I'm going to regroup the one group of 8 into the column over. And how many left over do I not have in that group of 8? 3. Is that blue? That's really light color. Let's try that one instead. All right, then we're going to add 1 plus 3 plus 1, and we're going to get 5. So this is 5, 3, base 8. Okay, it's the regrouping along the way that we're doing inside of the standard algorithm. Let's do the expanded algorithm. It's not the one I have written down, but it's the one I'm inclined to do at the moment for some reason. Right? So this is 3. Actually, let me do it with column addition. I think I like that one better for this particular numbers. 3, 8, and 1, 7. So, was it 1, 7? Sorry. 3, 4, and 1, 7. There we go. So column addition, we can move from left to right or right to left. It doesn't matter, but we're just adding the columns together. So for the 3 and the 1, I would get a 4. That's totally cool, and there would be nothing in that column if I'm going from left to right. And then I'm going to add the 4 and the 7, and I'm going to get 11. But remember, this is the 8s column, and this is the 1s column. So when I'm thinking about 8s and 1s, I have 11 to divvy up. That's 1 8 and 3 1s. Right? That's what 11 is. 1 8 and 3 1s. And then if we add together, we get that same 5 3 showing up with the subscript 8. All right, let's take a look at base 3. Base 3, we just don't have a lot to work with, 0, 1, and 2. And we're adding the number 1, 2, 1, 2, base 3, and 1, 1, 2, base 3. So standard algorithm, 1, 2, 1, 2, plus 1, 1, 2. We'll start in the 1s column. 2 plus 2 is 4. But in base 3, right, I break it into groups of 3. How many groups of 3 can I make out of 4 units? One group of 3, so 1 gets regrouped. And how many are left over? 1. Now we're going to add the 2's column, or the 3's column, the next column. 1 plus 1 plus 1 gives me 3. But 3 regroups into one group of 3 and 0 left over. Now we've got the 3 squareds column. I have 1 plus 2 plus 1, which gives me 4. 4 regrouped gives me how many groups of 3? 1 group of 3 and 1 left over. And then I have the 1 plus 1, which will give me 2. And this is in base 3. I'm going to do lattice for the other one on this one. So remember, I have to have the same number of boxes as I have digits. So I need 4 boxes because the first one has 4 digits. The second number is only 3 digits, but I still need the 4 boxes for the first one. Oh, that's not good. Let's try again. So something like that. We split them into diagonals. And again, it doesn't matter if we move left to right or right to left. So I'm going to go left to right on this one, but if you want to do the other way, you could. The 3 cubes column, my far left-hand side is just the number 1. And then I have 2 plus 1, which is 3. So it's 1, 3, and 0 ones. The 3's column now, I have a 1 and a 1, which gives me 2. And then in the 1's column, I have 2 plus 2, which gives me 4, which is 1, 3, and 1, 1. Is everybody good so far? This whole idea of regrouping is super, super important. And then we're going to add along diagonals. And I mentioned when I showed you this method before that you could end up having to regroup along your diagonals, and we will on this one. So that works out kind of nice to see an example. So on the far right, and you do have to move from right to left to finish this, you have the 1. And then I have 2 plus 1, which gives me 3. So I need to regroup the 1 over here for the 3, and I have 0 left over down here. The 3's squareds column is the 1 plus 0 that I'm on, so that's a 1. And then I have a 1 plus 1, which is a 2. So 2, 1, 0, 1, base 3. Any questions on that? Okay, we've done the most difficult stuff from this section. It's smooth sailing when we come next time to finish it up, all right?